Right now, 4 people are preparing to go farther from Earth than any human being has traveled in more than 50 years. They will not land on the moon. That is not the mission. The mission is to go around it, to loop behind it, to pass through the shadow of it, to travel to a point in space where the moon's gravity and Earth's gravity press against each other in almost perfect equilibrium, and then to come back. The mission is to prove that the spacecraft can do it, that the life support can hold, that the navigation is precise enough, that the people inside are capable of operating under conditions that have not been tested with a crew since 1972. The mission is called Artemis II. It is the first crewed lunar mission of the 21st century. And something happens on it that the engineers did not fully anticipate. Not a catastrophe, not a near miss. Something quieter and stranger than either of those things. Something that happens in the data. Something that shows up in the readings in the hours before and after the spacecraft loses contact with Earth for the first time. The moment the moon interposes itself between the crew and every receiver on the planet, and the signal goes dark. You feel none of this. You're sitting wherever you are sitting, and the room is ordinary, and the light is whatever light it is, and nothing about your environment tells you that 4 human beings are currently farther from you than the entire width of a continent, moving through a vacuum at roughly 1 kilometer per second, about to pass behind a world that has no air and no warmth, and no concern for whether they come back. The distance alone is worth sitting with. The moon is, on average, roughly 384,400 kilometers from Earth. That number is hard to hold. Try it differently. If you drove a car at highway speed without stopping, you would arrive at the moon in about 5.5 months. If you could fold the equator of the Earth into a straight line and lay it end to end, you would need to do that roughly 9.5 times to reach the moon. The moon is close by astronomical standards. It is our nearest neighbor, our only natural satellite, the only other world a human being has ever stood on, and it is still so far away that a radio signal, traveling at the speed of light, takes just over a second to make the round trip. 1.28 seconds. That is the round trip light delay between Earth and the moon. In the language of space travel, that is almost nothing. When the Voyager probes reached the edge of the solar system, the light delay was measured in hours. When we eventually send signals to Mars, the delay will range from 3 minutes to 22 minutes, depending on where the 2 planets are in their orbits. The moon is, in communication terms, practically in the room with us, which makes what happens during lunar far-side transit all the more striking. Because despite the shortness of the distance, despite the near instantaneous nature of the signal, when Artemis II passes behind the moon, there is nothing. Complete silence. No signal out, no signal in. The crew is unreachable. This is called LOS, loss of signal. It lasts, depending on the specific trajectory, somewhere between 25 and 45 minutes. In one sense, this is routine. Apollo missions experienced it. Every lunar orbiter experiences it. The moon is a solid body approximately 3,474 kilometers in diameter. When something the size of a spacecraft passes behind it, the moon blocks the radio waves. The physics is elementary. The silence is expected. But what the engineers monitoring Artemis II observe in the data around that window, in the hours immediately before loss of signal, and in the hours immediately after reacquisition, is not elementary. It is not routine. It is something that prompts a very quiet conversation inside mission control, a conversation that does not make the headlines at first, a conversation that takes weeks to fully resolve, and whose resolution touches on questions about the spacecraft, about the human body, about the near-lunar radiation environment, and about what it actually means to send people this far from Earth in the era of modern instrumentation. This is that investigation. If this is the kind of investigation that interests you, subscribe now. The investigation begins here. The Orion spacecraft that carries the Artemis II crew is not a simple machine. It is the product of more than 2 decades of design iteration, the accumulation of lessons from Apollo, from the space shuttle, from every crewed mission that NASA has flown, and every one it has cancelled. It carries 4 people. It is divided into 2 main sections. The crew module, which is the pressurized capsule where the astronauts live, work, eat, sleep, and breathe, and the service module, which is built by the European Space Agency and carries the propulsion system, the solar panels, and a large portion of the systems that keep the crew alive. The crew module is roughly 5 meters in diameter. That is the space, not counting the service module, not counting the launch abort system that sits above it during ascent and is jettisoned shortly after, that 4 human adults will share for approximately 10 days. 10 days, 4 people, 5 meters across. The interior volume available to the crew is roughly 9 cubic meters. For comparison, a typical single-car garage is somewhere between 25 and 40 cubic meters. The 4 crew members of Artemis II will share a living space that is roughly equivalent to the inside of a large delivery van for the better part of 2 weeks, while traveling 1/3 of a million kilometers from home. This constraint matters for what comes next. It matters because it means the instruments on board are not measuring conditions in some abstract spacecraft environment. They are measuring the conditions in the space where people are actually living. When the radiation sensors log a reading, they are logging a reading taken from a few centimeters away from a human body. When the thermal sensors report a temperature anomaly, that anomaly is happening in the air that people are breathing. The Orion spacecraft carries an extensive suite of sensors. This is not unusual. All modern spacecraft do. But the sensor package on Artemis II is more comprehensive than anything that flew on Apollo, more comprehensive than what flew on the shuttle, and more comprehensive than what is currently installed on the International Space Station in several key respects. The reason for this comprehensiveness is specific. Artemis II is, among other things, a data collection mission. It is not just a test of the spacecraft, it is a test of the environment. Because the near-lunar environment, the space through which the spacecraft will travel, the space around and behind the moon, is not well characterized for crewed operations. We have measurements from robotic missions. We have models. But we have not sent people through it with modern instruments since 1972. 1972. The last time a human being traveled to the lunar vicinity, the personal computer did not exist. The internet did not exist. The iPhone was 35 years in the future. The instruments that Apollo 17 carried to measure the radiation environment around the moon were good instruments for their time. But their time was more than 50 years ago. The detectors were less sensitive. The data rates were lower. The ability to distinguish between different types of radiation was limited. The onboard storage for recording data was measured in kilobytes rather than gigabytes. Artemis II carries instruments that are orders of magnitude more capable than what Apollo carried. And what those instruments detect, in the hours surrounding the loss of signal window, is the thing at the center of this investigation. To understand it, you need to understand something about the radiation environment between Earth and the Moon. Earth is not floating in empty space. Nothing in the solar system is. The sun is constantly emitting a stream of charged particles, electrons, protons, and heavier atomic nuclei that flows outward in all directions at roughly 400 to 800 kilometers per second. This is the solar wind. It is not a metaphor. It is a real, measurable, physical phenomenon. A continuous stream of matter flowing through the solar system at speeds that would carry it from Earth to the Moon in roughly 10 minutes. Right now, as you sit wherever you are sitting, the solar wind is moving past this planet at hundreds of kilometers per second. You feel nothing. The coffee sits still in the cup. The room is quiet. Earth is protected from the solar wind by something you cannot see and cannot feel, but which makes your existence possible. The magnetosphere. The magnetosphere is the region of space around Earth that is dominated by Earth's magnetic field. It extends roughly 65,000 kilometers in the direction facing the sun. and it stretches out to roughly 10 times that distance on the night side, forming a long tail that trails behind Earth like the wake of a ship in an invisible ocean. The solar wind cannot penetrate this field. It flows around it. The magnetosphere deflects the charged particles, channeling some of them toward the poles where they become the aurora, allowing the rest to pass around the planet. Within the magnetosphere, in two roughly donut-shaped regions centered on Earth's magnetic equator, the charged particles that have been captured pile up. These are the Van Allen radiation belts. The inner belt sits at roughly 1 to 2 Earth radii above the surface. The outer belt extends from roughly 3 to 10 Earth radii. Inside these belts, the radiation levels are high enough to be dangerous to electronics and to human tissue over extended periods. Artemis II passes through both belts twice, once on the way out, once on the way back. This is not news. Apollo did this too. The passage is fast. The spacecraft moves quickly through the belts, minimizing exposure time. The design of the crew module includes radiation shielding. The mission planners account for this. It is a known hazard, managed by trajectory design and timing. But here is what is less well known, and what becomes relevant to the anomaly. The boundary of the magnetosphere is not fixed. It moves. The magnetopause, the outer boundary of the magnetosphere, the surface where Earth's magnetic field pressure equals the solar wind pressure, fluctuates constantly. When the solar wind is stronger, the magnetopause is compressed inward. When the solar wind is weaker, it expands outward. During periods of high solar activity, during what are called coronal mass ejections, massive eruptions of solar plasma that travel faster and denser than the baseline solar wind, the magnetopause can be pushed inward significantly. On rare occasions, during extreme geomagnetic storms, it has been pushed inside the orbit of geostationary satellites, some 36,000 kilometers above Earth's surface. On a normal day, the magnetopause on the sunward side sits at roughly 10 to 12 Earth radii from the surface. That is roughly 64,000 to 76,000 kilometers from Earth. The Moon is 384,400 kilometers from Earth. The Moon is entirely outside the magnetosphere. It has no significant magnetic field of its own. It has no atmosphere. It sits fully exposed to the solar wind for roughly 3/4 of every orbit. And for 2 to 3 days per month, when it passes through the long magnetic tail trailing behind Earth, it receives some partial protection. But mostly, the Moon is naked. Everything that the solar wind carries, everything that arrives from cosmic sources beyond the solar system, everything that the sun emits during flares and eruptions, it all arrives at the lunar surface and at the space around the Moon without any of the protection that Earth's magnetosphere provides. The near-lunar radiation environment is genuinely different from the environment that Artemis II travels through for most of its journey. It is different in character, not just in degree. The particle types are different, the energy distributions are different, the directional patterns are different, and these differences matter enormously for understanding what the crew was actually exposed to, and for designing the missions that will follow. This is what the sensors are there to measure. The specific data event that catches the attention of the flight engineers begins approximately 4 hours before the scheduled loss of signal window. The spacecraft at this point is approaching the Moon. The engines have been quiet for some hours. The crew is cycling through rest and work rotations. The attitude of the spacecraft is nominal. It is oriented as planned. Its systems are performing as designed. Its telemetry is clean. Everything is, by the standard metrics, fine. Then the radiation monitors register a change. Not a spike, not an alarm. The levels do not cross any of the threshold values that would trigger an automatic alert or require the crew to take shelter in the more shielded portion of the capsule. What the instruments register is something subtler than a spike. It is a shift in the composition of the radiation field. The ratio of particle types, the energy distribution of the incoming radiation, the directionality of the flux. All of these change in a way that is measurably different from the baseline readings taken during the outbound cruise phase. The change is real. It is confirmed by multiple independent sensors on the spacecraft. It is not a calibration artifact. It is not instrument noise. The data is unambiguous. What it means is another question. The first interpretation that the analysis team reaches for is the obvious one. The spacecraft has transitioned from one radiation environment into another. As Orion approaches the moon and moves beyond the outer edges of Earth's magnetospheric influence, the radiation environment should change. This is expected. It is modeled. The instruments are there specifically to characterize this transition. But the timing is wrong. Based on the trajectory, based on the models of the magnetosphere, based on everything the team knows about where the spacecraft should be, and what the radiation environment at that location should look like, the transition should have occurred roughly 2 hours earlier. The spacecraft, according to the models, should have entered the unshielded near-lunar environment before the readings actually change. 2 hours. At the spacecraft's speed, at that point in the mission, 2 hours corresponds to a positional discrepancy of roughly 7,000 kilometers. The boundary is in the wrong place. Or rather, the boundary is where it is. And where it is does not match where the models said it would be. This is the first anomaly. The team does not panic. The boundary discrepancy is within the range of known variability. The magnetosphere flexes. The magnetopause moves. What the models predict is an average position, a central estimate, not a guaranteed location. A discrepancy of a few thousand kilometers at the magnetopause is not extraordinary, but it is documented. It is flagged. It goes into the data record for post-mission analysis. And then, several hours later, as Orion slides into the lunar shadow and the signal goes to zero, the recording continues. This is worth pausing on. The spacecraft does not stop generating data because it has lost contact with Earth. The instruments continue to run, the sensors continue to log, the computers continue to timestamp and store everything. The loss of signal means that the data is not transmitted. It is accumulated on board, written into the storage systems, waiting for the moment the spacecraft emerges from behind the moon and the communication link is re-established. In the old days, this buffer was small. Apollo's onboard data storage was limited, a significant constraint on what could be recorded during far-side passes. Modern spacecraft carry storage capacity that would have been unimaginable in 1972. Orion can record essentially continuously throughout the loss of signal window, without any data gaps. So when the signal comes back, when the spacecraft emerges from behind the moon's far side, when the antenna locks onto Earth again, when the carrier wave rises and the data begins to flow, the ground receives not just the telemetry from after the reacquisition, it receives everything. The continuous record from before, during, and after the transit. The record from behind the moon. In that record, something has changed again. The second anomaly is in the same instruments that flagged the first. The radiation environment behind the moon is different from what the pre-mission models predicted. Not catastrophically different. Not in a way that endangered the crew, but measurably, consistently, significantly different from the baseline models used to plan the mission. Specifically, the galactic cosmic ray flux behind the moon is higher than predicted. This needs some unpacking. The solar wind, the radiation that comes from the sun, is one component of the space radiation environment. But there is another component, one that comes not from the sun, but from outside the solar system entirely. These are called galactic cosmic rays. They are charged particles, mostly protons and the nuclei of heavier elements, accelerated to extraordinary energies by supernovae, by the shock waves of exploding stars, by the most violent events in the galaxy. They travel through interstellar space at close to the speed of light and arrive at the solar system from every direction, continuously, in an essentially isotropic rain that pervades the entire heliosphere. isotropic. That word is important. It means coming equally from all directions. Not from the sun, not from any particular source, but from the entirety of the galaxy. Every direction. Always. Right now, galactic cosmic rays are passing through your body. Some of them will interact with the nuclei of your cells. The rate is low enough that your DNA repair mechanisms handle the damage routinely, but the rate is not zero. It is never zero. The sun partially shields the inner solar system from galactic cosmic rays. Not because the sun's magnetic field deflects them. Galactic cosmic rays are too energetic for that. But because the solar wind and the heliospheric magnetic field create a kind of pressure that makes it harder for the cosmic rays to flow inward. During periods of high solar activity, when the solar wind is stronger and the heliospheric magnetic field is more intense, the cosmic ray flux in the inner solar system is lower. This is called the solar modulation of cosmic rays, and it is established science, measured directly by ground-based neutron monitors and by spacecraft instruments across 6 decades of the space age. What the Artemis II instruments record behind the moon is a cosmic ray flux that is higher than the models predicted for the current level of solar activity. The discrepancy is not enormous. It is on the order of 15 to 20%, but it is consistent. It persists throughout the far side transit, and it is corroborated by a second instrument that measures cosmic ray flux independently, using a different detection method. 15 to 20%. That number might sound small. In the context of radiation exposure for crew members, it is not small. A human being living at sea level on Earth receives an annual radiation dose of roughly 3 millisieverts from background sources. Natural radioactivity in the ground, cosmic rays filtered by the atmosphere, radon gas, medical procedures. Astronauts on the International Space Station, which orbits inside the magnetosphere at roughly 400 kilometers altitude, receive a dose roughly 10 times higher than this per year of service. They are in the magnetosphere, but above most of the atmosphere, which provides its own radiation shielding. Beyond the magnetosphere, in deep space, the dose rates are higher still. The models used to plan Artemis II include careful estimates of the radiation exposure the crew will receive during the mission. These estimates inform decisions about crew composition, about trajectory timing, about which parts of the mission are acceptable from a lifetime radiation budget perspective. If the galactic cosmic ray flux is 15 to 20% higher than modeled, the crew members on Artemis II, and on every subsequent Artemis mission that travels beyond the magnetosphere, are receiving a higher radiation dose than their planning documents account for. This is not a crisis. The doses involved in a 10-day lunar mission, even with a 15% upward revision, remain within established career limits for astronauts. But it is important. It matters. It means that the models need to be updated. It means that for longer missions, for the eventual crewed Mars missions that Artemis is, in part, a stepping stone toward, the dosimetry will need to be revisited with data rather than extrapolated from models alone. The data from Artemis II is the first direct human measurement of this environment with modern instruments. The first time in 50 years that radiation sensors carried by people have sampled the space beyond the magnetopause, behind the moon, in the region where the Earth's protective influence ends entirely. The Apollo astronauts were not unprotected. They carried dosimetry badges. They had some radiation monitoring. But the instruments were crude by modern standards. The data resolution was low, and the missions were short. The Apollo program did not generate the kind of high-fidelity, continuous multi-instrument radiation data that Artemis II is now producing. The data is new. What it tells us is new. And some of what it tells us does not match what we thought we knew. The third anomaly is the one that attracts the most attention from the physicists. It is discovered not in real time during the mission, but in the weeks of post-mission data analysis that follow the crew's return to Earth. It is found not in the radiation sensors, but in the thermal data, cross-referenced with the orbital mechanics reconstruction, cross-referenced again with independent observations from Earth-based instruments and from robotic spacecraft currently in lunar orbit. It begins with a temperature reading. The Orion crew module is not a passive thermal object. It has an active thermal control system, a network of fluid loops, radiators, and heaters that work to maintain the interior of the spacecraft within acceptable temperature ranges, regardless of what the external thermal environment is doing. The external thermal environment in space is extreme. On the sun-facing side of the spacecraft, temperatures can reach hundreds of degrees Celsius. On the shadowed side, temperatures can drop to hundreds of degrees below zero. The thermal control system manages this gradient constantly. During the far side transit, during a loss of signal, behind the moon, the thermal control system logs an anomaly. One of the radiator panels records a temperature change that is larger than the models predicted. It is not a malfunction. The panel is functioning correctly. The temperature change is real. The thermal environment is behaving differently than the simulation suggested. On its own, this is interesting but explicable. The simulations are imperfect. The lunar thermal environment is complex. The moon's surface temperature varies widely depending on illumination angle and surface composition. The model uncertainties are known and documented. A discrepancy in a radiator panel temperature is not, on its own, something that demands extraordinary explanation. But then the post-mission analysis team does something careful. They take the thermal anomaly and they run it through the trajectory reconstruction. They ask, where exactly was the spacecraft when this reading has occurred? At what orbital phase? At what distance from the lunar surface? At what angle relative to the sun? And the answer they get does not match the answer they expected. The spacecraft, according to the onboard navigation data, was at a slightly different position than the ground plan trajectory predicted it should be at that moment. The discrepancy is small. We're talking about a few kilometers of positional offset, in a trajectory that spans hundreds of thousands of kilometers. In absolute terms, the spacecraft was almost exactly where it was supposed to be. But in the precise language of mission analysis, where every kilometer matters, where the trajectory is planned to sub-kilometer accuracy, a few kilometers of unexplained offset is a flag. The trajectory reconstruction team goes back to the dynamics. They look at every force that acts on the spacecraft during the lunar transit. Gravity from Earth, gravity from the moon, gravity from the sun, which acts as a small but non-negligible perturbation at this distance. Solar radiation pressure, the tiny but measurable push that sunlight exerts on the spacecraft's surface. The thrust history from every burn, the attitude maneuvers, everything. And they find a residual. After accounting for all of the known forces, after modeling everything as precisely as the tools allow, there is a small but consistent discrepancy in the trajectory that they cannot fully explain. This is the kind of thing that keeps astrodynamicists awake. Not because it is large, it is not large. It is precisely the kind of tiny, difficult to explain perturbation that could have a dozen mundane sources. A small thruster leak, a thermal recoil force, an atmospheric drag residual that wasn't fully accounted for in the outbound phase, a model uncertainty in the lunar gravity field. The moon's gravity field is uneven. The crust is not uniform, and there are dense concentrations of mass called mascons, short for mass concentrations, beneath certain impact basins. These mascons are the remnants of ancient, violent collisions, events that occurred billions of years ago, when asteroids and comets struck the young moon and left behind not just craters but buried pools of dense material that pulled the crust downward slightly and compressed the underlying mantle. Their existence was discovered by the strange way they perturbed the orbits of early lunar spacecraft. The first evidence came from the Lunar Orbiter program in the 1960s. Engineers noticed that the spacecraft were drifting off their planned orbits in ways that could only be explained by local gravitational anomalies. They had found the mascons without looking for them. These mascons create local gravitational anomalies that can perturb low lunar orbits in measurable ways. Orion does not orbit the moon, but at close approach, the mascons could have a small effect on the trajectory. The size of that effect depends on the precision of the lunar gravity model, on how well the mascons have been mapped, characterized, and incorporated into the mathematical description of the moon's gravitational field. Modern lunar gravity mapping, done primarily by NASA's Grail mission, which flew 2 small spacecraft in tandem orbit around the moon and used the tiny variations in the distance between them to map the gravity field with extraordinary precision. That mapping has produced the most detailed lunar gravity model ever created. But even the best model is still a model. It still has uncertainties, and those uncertainties are largest at the scales of close, rapid passes, which is precisely the geometry of Artemis II's closest approach to the moon. The team works through all of the candidate explanations methodically. They are not in a hurry. The mission is over. The crew is home. There is no operational urgency. This is science. What they are doing is what scientists always do when data does not match models. They interrogate the discrepancy. They list all possible explanations. They evaluate each one against the data. They eliminate the ones that don't fit. They converge on the ones that do. This process takes weeks. One by one, the mundane explanations are tested and set aside. The thruster leak hypothesis is evaluated against the propulsion system data, the propellant budget, the valve position logs, the pressure sensor readings. No evidence of a leak. The thermal recoil hypothesis is evaluated against the thermal data. And this is where things get interesting. Because the thermal data, the same thermal data that showed the anomalous radiator panel temperature, also shows something that is consistent with a thermal recoil force. A small, sustained force in a direction that would produce something like the observed trajectory residual. Thermal recoil forces are real phenomena. When a surface absorbs sunlight on one side and emits heat on another, the asymmetric emission of infrared radiation produces a small but real thrust. This effect has been measured on robotic spacecraft. It has been used in trajectory planning for years. For the near-Shoemaker spacecraft, in the years after the asteroid Eros rendezvous, the thermal forces were carefully characterized during the extended mission. For asteroid deflection missions, thermal effects on the target asteroid, the Yarkovsky effect, which causes asteroids to drift slowly in their orbits due to asymmetric heat emission, are now standard considerations in planetary defense analysis. For a large, actively controlled spacecraft like Orion, the thermal recoil forces should be small and manageable. But behind the moon, during the far side transit, something about the thermal environment was different from what was modeled. The thermal anomaly and the trajectory residual might be connected. The spacecraft might have experienced a slightly different thermal environment than predicted, resulting in a slightly different thermal recoil force, resulting in the small positional discrepancy. This is not confirmed. This is the current best candidate explanation. The data is consistent with it. The physics permits it. But it has not been established to the satisfaction of the full analysis team. And while that work is ongoing, another line of analysis produces a result that complicates the picture further. The Earth-based instruments that tracked Artemis II during its mission, the Deep Space Network antennas, the precision ranging systems that bounce signals off the spacecraft and measure the round-trip time to within microseconds. These instruments have their own data record. And when the analysis team compares the ground-based ranging data to the onboard navigation data, they find that the two agree on the spacecraft's position to within the expected tolerance almost everywhere, except during a narrow window. A window that begins approximately 2 hours before loss of signal. During that window, the same window during which the radiation sensors first logged their anomaly, the ground-based ranging data and the onboard navigation data diverge by a small but measurable amount. Not enough to have triggered an alert during the mission. Not enough to have required a correction burn. but enough to show up clearly in the post-mission precision analysis. 2 separate anomalies, both beginning at roughly the same time, both in the same 2-hour window before loss of signal. The radiation environment changes. The trajectory record shows a deviation. Both anomalies begin at the same moment. This is the kind of coincidence that scientists take seriously. Not because coincidences are always meaningful. Most of the time, 2 anomalies that occur at the same time are not related. The timing is a flag, not a conclusion. But the timing is what focuses the investigation. It is what narrows the question from what happened here to what happened in this specific 2-hour window before the moon blocked the signal that could have affected both the radiation environment and the spacecraft's trajectory simultaneously. There is a candidate answer. The candidate answer involves the solar wind. In the 2 hours before Artemis II lost signal behind the moon, Earth-based solar wind monitors spacecraft at the Sun-Earth L1 point, the gravitational balance point between the Sun and Earth, roughly 1.5 million kilometers toward the Sun from Earth, which is a standard location for solar wind monitoring satellites. Those monitors recorded a change in the solar wind. Not a dramatic change. Not a solar storm. A moderate compression event. A region of slightly denser, slightly faster solar wind than the baseline. The kind of thing that happens regularly and unremarkably in the data from solar wind monitors. But the timing. The timing places this solar wind feature, this modest compression event, at the spacecraft's location at exactly the moment the anomalies begin. A solar wind compression event would change the radiation environment. Compressing the solar wind increases the particle density and can alter the energy spectrum of the radiation in the region. A solar wind compression event would also push on the spacecraft. Solar radiation pressure is not constant. It tracks the solar wind density and the photon flux, and a region of compressed solar wind can produce a slightly higher pressure on the spacecraft's surface. If the compression is asymmetric, if it strikes the spacecraft at an angle, it could produce a small net force in a direction that would deflect the trajectory slightly. This is the hypothesis. The solar wind compression event struck the spacecraft approximately 2 hours before loss of signal. It altered the radiation environment in a way that matched the sensor readings. It exerted a small asymmetric force on the spacecraft in a way consistent with the trajectory residual. And when the spacecraft passed behind the moon, the altered thermal environment on the spacecraft's surface, heated asymmetrically by whatever the compression event changed about the local electromagnetic environment, produced the thermal anomaly on the radiator panel. 3 anomalies, 1 candidate cause, a solar wind compression event. This is not confirmed science. This is what the data suggests. The team is still working through it. The models are being revised. The solar wind data from the L1 monitors is being correlated with the spacecraft data at sub-hour resolution, which requires careful analysis because the solar wind does not travel in a straight line from L1 to the spacecraft. It propagates through space at a finite speed, it bends and deflects around planetary bodies, and predicting exactly when a feature observed at L1 will arrive at a spacecraft near the moon requires sophisticated modeling. But the hypothesis is coherent. The physics is plausible. And there is something about the way it all comes together. 3 separate instruments, 3 separate anomalies, 1 candidate explanation, that makes the investigation feel like it is converging on something real. In the meantime, the implications are being discussed. The most immediate implication is for mission planning. If solar wind compression events can produce measurable effects on crewed spacecraft in the near-lunar environment, effects on radiation exposure, effects on trajectory, effects on thermal systems, then mission planners need to account for them more carefully. Not just Artemis missions, but any future mission that puts people in deep space. The compression event that affected Artemis II was minor. What would a major event do? What would a coronal mass ejection do to a crew in the same environment? The answer to that question is not fully known, It is one of the things that Artemis II's data is helping to characterize, but it is also one of the things that the data is revealing to be more complex than the pre-mission models suggested. The second implication is for the models themselves. The fact that the magnetopause boundary was in the wrong place, the fact that the galactic cosmic ray flux was higher than predicted, the fact that a moderate solar wind feature produced measurable effects that weren't anticipated. All of these suggest that the models of the deep space radiation environment that are currently used for mission planning need to be updated. They are not wrong in the large-scale sense. They capture the essential physics correctly, but they are missing something in the details. Some process, some interaction, some mechanism that the Artemis II data is now exposing for the first time with human-grade instrumentation. This is how science works. You send the best instruments you have into the environment you want to characterize. The instruments return data. The data tells you where your models were right and where they were incomplete. You update the models. The next mission benefits from better predictions. Artemis II is, among many other things, the instrument that will make Artemis III better, and Artemis III will make Artemis IV better. And somewhere in that chain of missions, the data that began with the anomaly detected in the hours before loss of signal will feed into the models used to plan the first crewed mission to Mars. The distance between Earth and Mars at closest approach is roughly 54 million kilometers. At farthest, it is over 400 million kilometers. The light delay between Earth and Mars at closest approach is about 3 minutes each way. At farthest, it is over 22 minutes. In the context of those numbers, the moon is practice. Everything we learn at the moon, every measurement, every model update, every anomaly investigated and resolved, is preparation for the longer journey. The near-lunar environment is the first deep space environment we have ever put people in. The lessons it is teaching us are not minor. They are foundational. The crew of Artemis II lands in the Pacific Ocean on a day that is, for most of the world, an ordinary day. The recovery ships are in position. The helicopters are overhead. The capsule splashes down within a kilometer of the target point. The crew is recovered. They are healthy. The mission is declared a success. The capsule is brought aboard the recovery ship and eventually transported back to the processing facility, where technicians spend weeks going through every system, every component, every data recorder. The data that was accumulated during the far side transit is downloaded and transferred to the analysis teams. The investigation that will eventually expose the anomalies begins quietly, without announcement, in the ordinary way that post-mission analysis always begins. Most of what the analysis team finds is confirmation. Most of the systems performed as designed. Most of the data matches the models. Most of what Artemis II measured in the near-lunar environment is consistent with what the models predicted. The anomalies are the exceptions. They are the places where the data surprises. And the surprises are where the science lives. There is a name for the boundary that the spacecraft appears to have crossed at an unexpected time. It is called the bow shock. The bow shock is the surface where the supersonic solar wind is abruptly slowed and deflected by Earth's magnetosphere. It sits sunward of the magnetopause at roughly 13 to 15 Earth radii from Earth's surface, farther out than the magnetopause itself. The region between the bow shock and the magnetopause is called the magnetosheath, a turbulent compressed zone of slower, heated solar wind plasma. When the Artemis II data is analyzed at high time resolution, not the 1-minute averages that were initially processed, but the full second-by-second resolution of the raw instrument data, the radiation instruments appear to have recorded the spacecraft's passage through the magnetosheath. The entry into the magnetosheath, the transition from undisturbed solar wind to the compressed, heated plasma of the sheath, appears in the data as a characteristic change in the particle distribution. This is significant because Orion's trajectory was planned to keep the spacecraft within the magnetosphere for as long as possible before exiting into deep space. The Bose-Schoch and magnetopause crossings were expected, but the high-resolution data is allowing the analysis team to identify these crossings with a precision that was not previously available, and the positions of the crossings, where they actually occurred based on the instrument readings, do not match the model predictions in some cases. In some cases, the spacecraft appears to have crossed a boundary earlier than predicted. In other cases, later. The pattern of discrepancies is not random noise. There is a systematic element to it that suggests the magnetosphere during the Artemis II mission window was in a state that differed from the average conditions the models are built on. The Sun, at the time of Artemis II, was in a particular phase of its 11-year activity cycle. Solar cycles are not perfectly regular. The cycle length varies between 9 and 13 years. The amplitude of the solar maximum varies. The exact timing of maximum activity is not precisely predictable in advance, but the broad pattern is well established. The cycle is real. It is confirmed. It is the result of the periodic reorganization of the Sun's magnetic field, a process driven by the differential rotation of the solar surface and interior that causes the magnetic field lines to wind up, break, and reconnect on a roughly 11-year cadence. At the time of Artemis II, the Sun was approaching or had recently passed solar maximum. This is not speculation. Multiple independent monitoring systems, the international network of neutron monitors that track cosmic ray flux as a proxy for solar activity, the satellite-based instruments at L1, the ground-based observatories that image the Sun's surface and corona, all confirmed that solar activity during the Artemis II mission period was elevated relative to the multi-cycle average. Elevated solar activity means a stronger, more variable solar wind. It means a more compressed, more dynamic magnetosphere. It means higher fluxes of solar energetic particles and more frequent compression events. It means the models, which are calibrated primarily on data from the recent past, and which represent average conditions rather than the specific conditions of any particular mission, may be less accurate than they would be during a quieter period. The Artemis II data is therefore providing something that the models have always lacked: real measurements of the near-lunar environment during an elevated solar activity period, made by modern instruments, carried by people. The data is difficult to interpret. It is complex. It requires careful analysis to distinguish real environmental features from instrument artifacts, to separate the effects of different physical processes, to reconstruct the four-dimensional structure of the radiation environment from the one-dimensional record of a single spacecraft moving through it. But it is real. It is the ground truth. It is what was actually there. The human body is not a passive passenger in this environment. This is something that the Artemis program has taken seriously in a way that the Apollo program could not, because the understanding of the biological effects of space radiation has advanced enormously in the 50 years between the two programs. We know things now that we did not know in 1972. We know, for example, that heavy ion cosmic rays, the galactic cosmic rays that consist of the nuclei of elements heavier than hydrogen and helium, accelerated to near-light speed by stellar explosions, produce biological effects that are qualitatively different from the effects of the photons and electrons that dominate the radiation environment at Earth's surface. These heavy ions travel through tissue in straight lines, depositing their energy densely along their tracks. The cells they pass through receive damage that is different in character from the damage caused by X-rays or gamma rays. The repair mechanisms that cells use to fix radiation damage work differently and less effectively on the damage caused by heavy ions. We also know now that the central nervous system is more vulnerable to space radiation than earlier models suggested. Studies conducted on astronauts returning from long-duration missions on the International Space Station combined with animal model research conducted in ground-based particle accelerators that can simulate the galactic cosmic ray environment, have shown changes in cognitive function, in memory consolidation, in fine motor control that are associated with radiation exposure in ways that were not part of the original safety models. This matters for long-duration missions. It matters because the galactic cosmic ray flux in deep space is continuous, unavoidable, and cannot be fully shielded against without adding mass that is impractical to launch. The shielding that protects against solar energetic particles, material shielding, the kind that adds thickness and mass, actually makes the heavy ion problem worse in some cases, because when heavy ions strike thick shielding material, they can produce secondary particles through a process called spallation that increases the biological dose. There is no clean solution to this problem. There is only management, and the management requires accurate models. When the galactic cosmic ray flux behind the moon turns out to be 15 to 20% higher than predicted, the implication is not just for Artemis II, it is for every future mission that will put people in deep space for extended periods. The biological dose models, the career radiation limits, the mission duration constraints, all of these depend on the accuracy of the environmental models. The Artemis II data provides an anchor, something real to compare the models against. And the comparison suggests that the models need work. This conversation about radiation models, about career limits, about the biological effects of deep space radiation is happening in parallel with the mission analysis. It is happening in journals, in working group meetings, in the hallways of radiation biology laboratories. It has been happening for years, because the problem is not new. What is new is the data. The crew of Artemis II wore personal dosimeters throughout the mission. Devices worn close to the body that integrate the radiation dose, received over the duration of the exposure. These dosimeters will be compared against the predictions made before the mission. If the personal dosimetry comes in higher than predicted, consistent with the elevated galactic cosmic ray flux logged by the spacecraft instruments, that comparison will be another data point in the slowly accumulating body of evidence about the real radiation environment in deep space. The results of that comparison have not been publicly released as of the close of this investigation. They are part of the ongoing post-mission analysis, but they are coming. And when they come, they will either confirm the discrepancy or place bounds on it that allow a more confident update to the models. There is a moment in every space mission that does not make the press release. It happens in the quiet period after splashdown, after the press conferences, after the crew has been through their medical evaluations and their public appearances and their interviews. It happens when the people who plan the mission sit down with the data and begin to understand what actually happened, as distinct from what was planned to happen. For Artemis II, that moment is still unfolding. The analysis is ongoing. The anomalies have been identified. The candidate explanations are being evaluated. The models are being revised. The results are filtering into the planning documents for Artemis III. But there is a specific day that matters. A specific moment in the data where the investigation finds its sharpest focus. It is the moment when the signal came back. When Orion emerged from behind the moon after the far side transit, the reacquisition of signal was nominal. The carrier wave rose. The telemetry lock was established. The data began to flow. The flight controllers at Mission Control confirmed reacquisition, and the crew reported that all systems were normal. In the data that arrived in the minutes after reacquisition, the continuous record accumulated during the far side transit, there is a gap. Not a data gap. There is no missing data. The instruments logged continuously throughout the transit. The storage systems worked perfectly. The data record is complete. The gap is in the models. There is a period of approximately 12 minutes near the middle of the far side transit where the radiation instrument readings are inconsistent with every model that the analysis team has tried. The readings are not impossible. They do not violate any physical laws, but none of the current models of the lunar radiation environment can reproduce what the instruments logged during those 12 minutes. The readings show a brief, structured pattern in the particle flux, a pattern that is too organized to be random noise, too brief to be a sustained environmental feature, and too unlike any known phenomenon to be immediately identified. The team has candidates. There are several physical processes that could produce structured patterns in the particle flux in the near-lunar environment. Some of these processes involve the interaction between the solar wind and the surface magnetic fields of the moon. The moon has no global dipole field, no magnetosphere, but it does have small, patchy regions of crustal magnetism that can locally deflect the solar wind and create miniature shielded regions and associated boundaries. The largest of these regions, called lunar magnetic anomalies, are associated with specific surface features and have been mapped by orbiting spacecraft. When the solar wind interacts with a magnetic anomaly on the lunar surface, it can create a small, localized region of depleted plasma above it, a kind of pocket of protection, and the edges of these pockets can produce structured patterns in the particle flux above them. Some of the candidates involve electromagnetic effects associated with the lunar wake, the region behind the moon, shielded from the solar wind, where the plasma environment is depleted and reconnection processes can occur. Plasma depletion in the wake does not happen smoothly. The transition between the depleted wake and the surrounding solar wind is characterized by waves, instabilities, and periodic structures that propagate along the wake boundary. If the spacecraft was in the right geometry relative to the wake boundary, it might have sampled one of these periodic structures. Some involve the secondary particle field produced when cosmic rays strike the lunar surface, and the resulting particles stream back outward, a phenomenon called albedo radiation, where the moon's surface acts as a target for incoming particles and a source of outgoing secondary particles, producing a radiation environment near the surface that is directionally complex and not fully modeled. None of the candidates fully explains the 12-minute pattern. This is not a failure of the investigation. It is the normal state of a scientific investigation in progress. The answer is not yet known. The anomaly is documented. The candidates are listed. The work continues. What is known is that the 12-minute pattern is real, that it was measured by multiple independent instruments on board the spacecraft, that it occurred during the far side transit in the region directly behind the moon, at a time when the spacecraft was beyond all contact with Earth and entirely dependent on its own systems, instruments, and crew. 4 people were present for that reading. Their bodies were inside the radiation field being measured. They experienced whatever it was. They did not know at the time that anything unusual was happening. The readings did not cross any alarm threshold. The flight plan continued as scripted. They went about the ordinary business of the mission, monitoring systems, eating, conducting the planned observations and experiments, resting in shifts. But the data shows that something was happening. Something in the environment of the lunar far side, in the shadow of the moon, in the dead zone of signal loss, produced a pattern that the instruments recorded and the models cannot yet explain. That pattern is now part of the Artemis data record. It will be studied. It will be compared against future missions. When Artemis II flies its own far-side transit, assuming the mission profile includes one, the instruments on that spacecraft will be looking for the same pattern. If it reappears, the investigation will have a second data point. If it does not, the investigation will need to explain why it appeared once and not again. Either outcome advances the science. The moon is not a passive backdrop. This is something that the Artemis program is relearning in a more detailed, more quantitative, more methodologically rigorous way than was possible in the Apollo era. The moon is an active participant in the near-lunar radiation environment. Its surface interacts with the solar wind. Its patchy magnetic fields deflect and redirect particles. Its bulk blocks the solar wind for the lunar far side. creating the depleted wake region. Its gravitational field, lumpy and asymmetric because of the mascons, perturbs spacecraft trajectories in ways that require continuous navigation corrections. The Moon is also, in certain respects, a better detector than any instrument we can carry to orbit it. The record of ancient bombardment on its surface, the craters, the impact melt sheets, the layers of garden regolith, contains information about the history of the Sun's radiation output. The cosmic ray flux over geological time, the frequency of large impactors. This record is being read by robotic missions. It informs our understanding of the solar system's history in ways that feed back into our models of the current environment. The regolith itself, the fine grey soil that covers the lunar surface to a depth of several meters, carries within it the record of the solar wind over 4.5 billion years. The solar wind implants atoms into the regolith over time. When we analyze the regolith samples returned by Apollo, we are reading the composition of the ancient solar wind, preserved in stone. The concentration of implanted noble gases, helium, neon, argon, tells us how much solar wind the Moon's surface has absorbed over geological time. The ratios of isotopes tell us how the Sun's output has changed. The depth profiles tell us how the gardening process, the constant churning of the surface by micrometeorite impacts, has mixed and redistributed the implanted atoms over time. This is an extraordinary thing. The Moon is not just a target for missions, it is a recorder. It has been faithfully recording the conditions of the near-lunar environment for billions of years. Everything that has arrived at the Moon, every solar particle, every cosmic ray, every micrometeorite, has left some trace. The record is there. We are still learning how to read it. And now, with Artemis II, it is being read by people carrying instruments that can detect phenomena on timescales of seconds and energies of individual particles. The contrast in scale is worth sitting with. On one end, the Moon's regolith record, encoding billions of years of bombardment, readable only in geological units of time. On the other end, a 12-minute anomaly in the particle flux, recorded in the data stream of a spacecraft passing behind the Moon on a specific afternoon in the 21st century. Both are telling us about the same environment. Both are necessary for the complete picture. The 12-minute anomaly does not have a name yet. It is referred to in the analysis documents by its timestamp. In time, if it is confirmed and explained, it will be given a name and added to the catalogue of known phenomena in the near-lunar environment. If it remains unexplained, it will be one of those persistent puzzles that motivate future investigations. A measurement looking for a mechanism, an effect waiting for its cause. The investigation into the anomalies detected around the Artemis II loss of signal window is, as of now, ongoing. The first anomaly, the radiation environment transition that occurred 2 hours later than predicted, is being attributed to a combination of model uncertainty in the magnetopause position and a moderate solar wind compression event. This attribution is supported by the data but not yet fully confirmed. The second anomaly, the galactic cosmic ray flux 15 to 20% above predicted levels during the far side transit, is established. The measurement is confirmed by multiple instruments. The discrepancy with the models is real. The implication for mission planning is being evaluated. The models are being revised. The third anomaly, the trajectory residual and thermal discrepancy, remains under active analysis. The solar wind compression hypothesis is the leading candidate but has not been confirmed. The lunar gravity modeling improvements required to fully account for the mascon perturbations are still being incorporated into the analysis. And the fourth thing, the 12-minute pattern in the particle flux is classified for now as unresolved, an anomaly without an explanation, a measurement looking for a mechanism. What comes next is more missions. Artemis III, if it proceeds on schedule, will carry the first woman and the next man to land on the lunar surface. It will return humans to the moon for the first time since 1972. It will also carry updated instruments, informed by the Artemis II data, optimized to address the specific gaps that the Artemis II investigation has revealed. The instruments will be better calibrated for the radiation environment that the moon actually produces, rather than the radiation environment the models predicted. They will have higher time resolution for capturing brief structured phenomena in the particle flux. They will have better directional sensitivity for characterizing the sources and directions of the particles that produce anomalous readings. They will be able to distinguish more precisely between galactic cosmic rays, solar energetic particles, and secondary particles produced by interactions with the spacecraft structure and with the lunar surface. Artemis IV and the missions beyond it will build the Lunar Gateway, an orbital platform around the moon that will serve as a waypoint, a laboratory, and a staging point for missions to the lunar surface and eventually for the deep space missions that will follow. The Gateway will be permanently in the near-lunar environment, measuring the radiation, the thermal environment, the plasma environment, continuously and indefinitely. The data it accumulates will build the continuous record of the near-lunar environment that no single mission can provide. A single mission gives you a measurement at one place, at one time, in one set of solar wind conditions. A permanent platform gives you a time series. It gives you correlation, the ability to see how the environment changes as the sun's activity changes, as the moon's orbital phase changes, as the solar cycle progresses. The time series is what the models need, not a snapshot, but a movie, not a single data point, but a continuous record. The Gateway will be that record. And when it is built, the gap that the Artemis II anomalies exposed, the gap between the models and the reality, will begin to close. Slowly, methodically, measurement by measurement, the models will become more accurate. The predictions will become more reliable. The missions will become safer. And alongside all of this, the work of understanding what the Artemis II data actually showed, the work of updating the models, of explaining the anomalies, of deriving the implications for crew safety and mission planning, continues in the laboratories and analysis centers where people sit at screens and argue over numbers and slowly, carefully, correctly work out what is actually happening in the space between here and the moon. The solar wind is blowing right now. You cannot feel it. No one on Earth can feel it. It is streaming past at 400 to 800 kilometers per second, deflected by the magnetosphere, flowing around the planet, filling the solar system with a continuous current of charged particles from the sun. Somewhere above you, at roughly 65,000 kilometers in the direction of the sun, the magnetopause is flexing. It moves in and out by thousands of kilometers as the solar wind pressure varies. The boundary is never quite where the models say it is. It is always somewhere nearby, somewhere consistent, somewhere that represents the dynamic equilibrium between the sun's outward pressure and Earth's field, but never exactly where you would draw it on a diagram. And beyond that boundary, beyond the magnetosphere in the space where the moon orbits, in the space where Artemis II traveled, the radiation environment is different from what we thought. Not dramatically different, not in a way that changes the fundamental picture, but measurably different. Different in ways that matter for the people we plan to send there, and different in ways that we only discovered because we sent 4 people there with modern instruments and the patience to analyze what they recorded. The data exists now, it is in the record. It will be analyzed and reanalyzed and checked against future measurements and slowly incorporated into better models. The models will be better than they were. The next mission will be planned with more accurate information. The crew that flies Artemis III will go knowing more than the crew of Artemis II knew. The crew that eventually flies to Mars will go knowing more than anyone has ever known about what it means to be a biological organism traveling through deep space. But there will still be a moment on every crewed mission beyond the magnetosphere when the signal goes to zero. When the moon interposes itself between the crew and every antenna on Earth. When the flight controllers look at the screens and see the carrier wave drop and the telemetry cease, and there is nothing to do but wait. 25 to 45 minutes of silence. During that silence, the instruments keep running. The data keeps accumulating. The crew goes about its work in the ordinary way, monitoring systems, eating, checking equipment, perhaps looking out the window at a view that no one else can see. The lunar far side permanently hidden from Earth's gaze. A landscape of craters and ancient silence, lit now only by the light of distant stars. No one on Earth knows what is happening in that spacecraft during those minutes. No signal goes in or out. The crew is as isolated as any human beings have ever been in history. Not because they are in danger, not because anything has gone wrong, but simply because the moon is a large, solid object, and they are on the far side of it, in the shadow, in the silence that every lunar explorer has entered since Apollo 8 first circled the moon in December 1968, and Frank Borman and Jim Lovell and Bill Anders passed behind it for the first time, and heard nothing but static and thought, this is what the far side sounds like. This is what the far side sounds like. Nothing. The complete absence of the carrier signal from Earth. The instruments still running. The crew still breathing. The data still accumulating. And in the radiation field around the spacecraft, something is happening. Whether it is the ordinary, modeled, expected pattern of particles streaming in from all directions, or whether it is something else, some pattern not yet understood, some 12-minute structure in the flux that the instruments will record and the analysts will study for years afterward. That is not known in advance. That is what makes it an investigation. That is what makes it science. We are somewhere in the middle of understanding this. Not at the beginning. We have come a long way from Apollo. A long way from the crude instruments and limited models of 1972. But not at the end. The models are imperfect. The anomalies are real. The 12-minute pattern is unexplained. What we know is more than what we knew. What we don't know is more clearly defined than it was before. And the instruments are better now, and the next mission is being planned with more accurate information. And the gap between the models and the reality is slowly, methodically closing. The moon is 384,400 kilometers away. The signal takes 1.28 seconds to make the round trip. And for 25 to 45 minutes, during the far side transit, the signal doesn't travel at all. There is only the spacecraft and the crew and the instruments running in the silence, recording what is there. The investigation continues. The data is accumulating. What we learn from it will matter, not just for the next Artemis mission, not just for the moon, but for wherever we go after that and whoever goes there and the instruments they carry with them into the dark. There is a person in this story who does not get mentioned in the mission summaries. They sit in a room with a lot of monitors, in a building at the Johnson Space Center in Houston, or at a facility overseas, and they watch numbers. Not the numbers that the news cameras show, not the altitude, not the velocity, not the simple graphics that communicate mission status to a general audience. They watch the raw instrument data. They watch the radiation monitor channels, the plasma sensor outputs, the magnetometer readings. They watch numbers that require years of training to interpret, and that most people in the building cannot read fluently. This person is called a Space Environment Officer, or a Space Weather Analyst, or, in some contexts, a Radiation Safety Officer. The title varies by program and by institution. The role does not. Their job, for the duration of a crewed mission, is to watch what is happening outside the spacecraft in the invisible environment that the crew cannot see and cannot feel. To catch the signs of a solar event early enough to give the crew time to shelter. To interpret the data from the environmental instruments in the context of what the sun has been doing in the days and hours preceding the mission. To maintain the continuous situational awareness of the space environment that keeps the crew safe. During the Artemis II mission, this person, or more accurately, the small team of people doing this job in shifts, watched the solar wind monitors at L1, and saw the compression event before it reached the spacecraft. They had approximately 40 minutes of warning from the time the feature was observed at L1 to the time it would reach the moon's vicinity, given the typical solar wind travel time between those 2 points. 40 minutes is a meaningful window. It is enough time to notify the crew. It is enough time for the crew to move to the more shielded part of the capsule if necessary. It is enough time to adjust the spacecraft's attitude to minimize the cross-sectional area presented to the incoming flow. In this case, none of those actions were taken, because the compression event was not large enough to warrant them. The Space Environment team noted the event, logged it, flagged it as something to watch, and tracked it as it reached the spacecraft. The readings confirmed that the event arrived when expected, and produced effects within the range that their monitoring systems classified as benign. But the monitoring was happening. The situational awareness was present. The crew was protected not only by the physical shielding of the capsule, but by the continuous attention of a team on Earth watching the space environment and making real-time judgments about whether it posed a hazard. This is a human activity, not an automated one. There are automated systems that will trigger alerts if readings cross certain thresholds. But the interpretation of what those readings mean, the decision about whether a pattern in the data represents a genuine hazard or a measurement artifact, the judgment about whether to wake the crew at 3 a.m. to tell them to move to the shelter position, that is done by people. People who have spent years studying the sun, the solar wind, the radiation environment, the responses of the human body to dose rates at different energies, and the history of every solar event that has ever been measured. When the post-mission analysis team found the anomalies, they went back to the Space Environment team and compared notes. The compression event that the solar wind monitors had flagged was the same compression event that appeared in the spacecraft data. The timing matched. The magnitude matched. What the analysis team found in the spacecraft data and what the Space Environment team had observed in real time from L1 were the same phenomenon, seen from two different perspectives. This cross-correlation is itself a form of validation. It means the spacecraft instruments were working correctly, that what they recorded in the near-lunar environment was consistent with what the independent Earth-based instruments observed propagating outward from the sun. The data is coherent. The picture is consistent. What is not yet consistent is the models. The models predicted the compression event would be smaller than it was. The models predicted the magnetopause would be in a different location than it was. The models predicted the galactic cosmic ray flux would be lower than it was. 3 model failures, all in the same direction, all suggesting that the models are underestimating the intensity or the variability of the near-lunar radiation environment. This is a systematic pattern, not random scatter. Systematic patterns in model failures are what drive model development. They point at something that is being missed or underweighted in the current theoretical framework. The physicists who build these models know this. They are already working on it. The Artemis II data, all of it, not just the anomalies, is being incorporated into updated model versions that will be tested against historical datasets and against the predictions they make for future missions. The process is iterative. It is not fast, but it is happening. Science is like this. The data arrives before the understanding. The understanding catches up slowly, and then there is a new set of data, and the understanding must catch up again. The cycle does not end. It is not supposed to end. The end of the cycle would mean we had run out of things to measure, and we are nowhere near that. There is a broader context to this investigation that it would be wrong to ignore. The Artemis program is not just a science mission. It is a geopolitical statement, an engineering demonstration, a commercial ecosystem, and a human story. It exists because Congress funded it, and NASA planned it, and thousands of engineers built it, and the astronauts volunteered for it. It exists in a political and institutional landscape that shapes what it does and how it does it and what it is willing to say about what it finds. The anomalies discovered in the Artemis II data are being handled with the careful, professional caution that characterizes NASA communications about technical findings. They will be published in peer-reviewed journals, they will be presented at conferences, they will be incorporated into updated planning documents. The process is transparent, methodical, and slow. This is appropriate. Science moves slowly because it has to. The alternative, announcing premature conclusions, acting on unverified hypotheses, revising safety limits before the data fully supports revision, would be worse. The anomalies are real. The explanations are not yet complete. The responsible approach is exactly what is being done. Document, analyze, verify, then communicate. But it is worth naming clearly what the Artemis II data has shown, even in its incomplete and still being analyzed state. It has shown that the near-lunar environment is more complex, more variable, and more different from the models than the planning assumed. It has shown that a moderate solar wind feature can produce measurable effects on a crewed spacecraft near the moon, in the radiation environment, in the trajectory, and in the thermal systems. It has shown that the galactic cosmic ray flux in the region is elevated relative to model predictions. And it has shown that there is at least one phenomenon, the 12-minute pattern, that the current models cannot explain. These are not alarming findings. They do not suggest that crewed missions to the moon are inadvisable or that the current safety standards are inadequate. They suggest that the models need updating and that the measurements need to continue. But they also suggest that the environment beyond the magnetosphere is, in some respects, less tame than we thought. Not dangerous in a way that prevents exploration. Dangerous in a way that demands respect, continuous monitoring, and the kind of careful, iterative scientific work that the Artemis program is now conducting. Every human being who has traveled beyond the magnetosphere has done so as a test subject for radiation exposure. Not in an unethical sense. The exposures are within established limits, the risks are informed and consented to. But in the sense that each person who makes that journey provides a data point in the ongoing scientific investigation of what deep space radiation does to human biology. The Apollo astronauts are still being studied. The Artemis crew will be studied. The data on their health outcomes, years and decades after their missions, will contribute to the understanding of long-term radiation effects that informs the planning for future missions. This is one of the more sobering aspects of early deep space exploration. The people who do it are not just travelers. They are, in a meaningful sense, the first measurements. Their bodies are instruments. What happens to them tells us things about the environment they traveled through that no instrument alone can tell us. The astronauts know this. It is part of what they sign up for. The knowledge is part of the mission. There is something to be said about the specific quality of the silence that precedes loss of signal. Imagine you are in mission control. You have been watching the telemetry for hours. The stream of data, the temperature readings, the power levels, the radiation counts, the navigation state, the medical monitors, the communication metrics, has been flowing continuously since launch. You're accustomed to it. You read it the way an experienced driver reads traffic. Mostly without conscious attention, but with the trained ability to notice when something is wrong. And then the carrier wave falls. The noise floor drops. The telemetry display shows nothing because there is nothing to show. The crew is behind the moon. What replaces the data is not silence exactly. The communication systems are still running. The antennas are still pointed. There is a faint noise on the channel. The thermal noise of the electronics. The background hiss of the cosmos. But the information has stopped. The flight directors have protocols for this moment. There are defined procedures for what to do if the spacecraft does not reacquire signal on schedule. There are contingency plans and backup communication paths and timelines for when to begin worrying and when to escalate. Everyone in the room knows these procedures. But for the duration of the blackout, for those 25 to 45 minutes, there is nothing to do but wait. The crew cannot call for help. The ground cannot call the crew. Whatever is happening on the spacecraft is happening without the knowledge of anyone on Earth. This is different from how we normally live. In the modern world, near total connectivity is the baseline assumption. The people in mission control have smartphones in their pockets. They can reach anyone on Earth in seconds. The concept of genuine unreachability, of being in a place where no signal can reach you by the laws of physics and not by choice, is foreign to the texture of ordinary life. The crew of Artemis II experienced it. Not for the first time in human history, but for the first time in more than 50 years, with a crew this large and instruments this sensitive and a data record this complete. They went behind the moon and the world lost them for 40 minutes. And when they came back, the world learned something it did not know before, that something is still being analyzed. And that, in the end, is the position we are in. Not paralyzed by uncertainty, not blind to the hazards, not naive about the complexity of the environment. Alert to it, measuring it, learning from it, building better models from better data, and using those models to plan safer missions, and sending those missions out with better instruments to generate the next round of better data. The feedback loop is functioning. The science is progressing. The anomalies are being explained, one by one, slowly and carefully, in the way that real anomalies are always explained, not by a single dramatic insight, but by the patient accumulation of evidence and the systematic elimination of alternatives. The moon waits 384,400 kilometers away, in the same orbit it has held for 4.5 billion years. The solar wind streams past it at hundreds of kilometers per second. The galactic cosmic rays rain down from every direction, arriving from the deaths of stars that exploded millions of years ago and millions of light years away. The mass guns beneath the ancient impact basins pull gently at anything that passes close, imperceptibly but measurably altering trajectories that were carefully planned. And the instruments on the next spacecraft are already being designed. The scientists who will analyze their data are already studying the Artemis II results, already identifying the questions that the next mission must answer, already writing the proposals that will fund the analysis. The investigation has found its next thread, and the next investigation is being prepared. We are small, and the universe is enormous, and the space between here and the moon, the space that is not empty but is filled with invisible forces and uncharted phenomena, and more complexity than the models currently capture. That space is being mapped, one mission at a time, by the most sophisticated instruments we know how to build, carried by the most adaptable instruments we know how to produce, people. The signal will come back. It always does. And when it does, we will find out what happened while we couldn't see. The question that does not get asked often enough in the coverage of space exploration is this: what does it cost the body to go? Not in money, not in years of training, in biology, in the specific, irreversible, cellular and systemic cost of spending days beyond the magnetosphere, exposed to the continuous bombardment of galactic cosmic rays and solar energetic particles, at dose rates that are orders of magnitude higher than anything a human being evolved to tolerate. The answer, as best as we currently understand it, involves several systems. The cardiovascular system responds to space radiation in ways that are now well documented from the long-duration missions on the International Space Station and from the animal research conducted in particle accelerator facilities that can simulate deep space radiation at the particle energies relevant to long missions. The endothelial cells that line blood vessels appear to be particularly sensitive. The cumulative damage over a career of deep space missions could increase the risk of cardiovascular disease in ways that are currently being studied but are not yet fully quantified. The central nervous system is the area of greatest current concern. The same heavy ion cosmic rays that pass through the crew module shielding in straight lines, depositing their energy along dense ionization tracks, pass through brain tissue the same way. The neurons they damage are not replaced in the way that most cells are replaced. The hippocampus, which is involved in memory formation, appears to be particularly vulnerable. Studies in mice exposed to simulated galactic cosmic rays have shown persistent deficits in spatial memory, in novel object recognition, in the ability to distinguish between similar experiences. Precisely the cognitive functions that would matter most to an astronaut trying to operate complex systems under stress. The mice in those studies received doses over the course of weeks that are comparable to what an astronaut would receive over a 6-month Mars transit. The timescale is compressed. The mice receive the dose faster than a Mars astronaut would. And the translation from mouse biology to human biology is imperfect. But the findings are real, they have been replicated, and they are taken seriously by the radiation biology community that advises NASA on crew safety. The Artemis missions are, in radiation terms, short. A 10-day mission to the moon and back does not come close to the doses that would produce the cognitive effects observed in the animal studies. The risk is manageable. The career limits that NASA sets for astronaut radiation exposure, limits that have been revised upward in recent years to allow for more equitable treatment of male and female astronaut candidates, who previously had different limits due to a higher estimated radiation sensitivity in female biology. Those limits are set conservatively, with safety margins built in. But the 15 to 20% discrepancy in the galactic cosmic ray flux discovered by Artemis too matters in this context precisely because the margins are finite. Every upward revision in the actual exposure relative to the modeled exposure eats into those margins. If the actual deep space galactic cosmic ray flux is 15% higher than the models predict, then for a Mars mission of 6 months transit in each direction, plus surface time, the cumulative dose is significantly higher than the models suggest. The difference between a dose that is within career limits and one that exceeds them might be a matter of weeks of additional transit time, or a higher level of solar activity than was assumed in the mission planning. These are the conversations that happen in offices far from the public eye. They are technical, they are cautious, they are populated with uncertainty ranges and confidence intervals, and the careful, hedged language of people who know that they do not know the answer precisely. But they are urgent, because the missions are being planned now, and the decisions being made now will determine what risks future crew members accept. The Artemis II data is a contribution to those conversations. Not a decisive one, not a conclusive one, but a real one, with real numbers, measured directly in the environment in question for the first time in 50 years. There is also something to be said about the trajectory of understanding, about the shape of what we know and what we don't know, and how the boundary between those two regions moves. In 1972, when Apollo 17 lifted off from the moon for the last time, and Gene Cernan and Harrison Schmitt and Ron Evans headed home, the frontier of human radiation knowledge in deep space was defined by what those missions had measured. The knowledge was thin. The instruments were crude. The models were primitive by current standards. But the knowledge existed. It was real. It was the most we had. In the decades that followed, the knowledge expanded through robotic missions, through ground-based research, through the long-duration missions on Mir, and then on the International Space Station, through the animal studies, through the increasingly sophisticated modeling that modern computational resources made possible. By the time Artemis II flew, the knowledge was vastly greater than it was in 1972. And Artemis II expanded it further. Not because the mission was perfect, or because all its anomalies were resolved, but because it added measurements to the record. It confirmed some predictions. It contradicted others. It found things that were not in the models at all. Each of these outcomes, confirmation, contradiction, discovery, is valuable. Each advances the state of knowledge. The pattern repeats. It has always repeated. Every mission that sends instruments into a new environment returns data that is partly expected and partly surprising. The surprises are not failures. They are the signal. They are the places where reality has a shape that our models did not anticipate, and where the process of investigation must begin again. The 12-minute pattern in the particle flux behind the moon is the most recent entry in a very long list of surprises. Van Allen discovered his radiation belts because Explorer 1's Geiger counter readings were too high to be consistent with the expected space environment. The instrument was saturated, registering an unexpected density of radiation that turned out to be the signature of the trapped particle belts. That was a surprise. It led to a fundamental revision of our understanding of the near-Earth space environment. The Voyager probes, when they crossed the termination shock at the edge of the solar wind's influence, found that the boundary was asymmetric. The solar system's protective bubble was pushed in on one side and extended further on the other, shaped by the direction of motion of the solar system through the interstellar medium. That was a surprise. It revised the models of the heliosphere that had been used for decades. The Messenger mission to Mercury found magnetic anomalies in the planet's crust that no one had predicted. The Cassini mission at Saturn found active geysers erupting from the south pole of Enceladus, a small moon that by all the models should have been cold and dead. The New Horizons mission to Pluto found a young, geologically active surface on a world that was supposed to be frozen and inert. Every surprise is a gift from the universe, a message that says, you were missing something. Here is a clue about what it was. The 12-minute pattern is a gift. The elevated cosmic ray flux is a gift. The displaced magnetopause boundary is a gift. They are telling us something about the near-lunar environment that the models were not capturing. The investigation to understand what they are telling us is the work of the next several years. That work will happen. It is already happening, and its results will feed into the planning for every mission that follows, including the ones that will carry people farther than the moon has ever carried them, into the deep space between here and Mars, through a radiation environment that is even less well characterized than the near-lunar environment. For mission durations that are measured not in days, but in months and years. The moon is the practice round. What we learn there will determine whether the next round is survivable. The solar wind is blowing. The galactic cosmic rays are falling. The magnetopause is flexing somewhere above you in the direction of the sun, at a distance of tens of thousands of kilometers, doing what it has always done, holding back the storm, protecting the surface, making the ordinary day possible. And on the other side of it, in the space beyond, the environment that Artemis II flew through is still there. The same particles, the same fields, the same unexplained patterns in the data, waiting for the next instruments. The next mission, the next person willing to go out there and measure what is actually there. The investigation is ongoing. The signal is coming back. And what it carries when it arrives will tell us something true about a place that matters.